Scanning tunneling microscopy, a close look at surfaces, atoms, and the electronic properties of nanostructures. The continuous development of many high-tech products such as mobile phones, digital cameras, memory sticks and PCs is characterized by an ever-shrinking size of the product. Yet the technical specifications such as memory size, resolution and speed of operation keep increasing at a high pace. These products offer more and more functionalities and better performance for less money. How is this possible, and what drives the technological improvement? Size matters. The smaller, the better. Let's have a closer look at the inside of a PC. Nowadays, 200 gigabytes of information can be stored on a size of your thumbnail. This high storage density indicates that a tiny area of 100 times 100 atoms is sufficient to store a bit of information. A human thumb is 1 to 2 centimeters wide. A hair has a diameter of 10 millionths of a meter. A metal atom has a diameter of 0.25 nanometers. Thus, a row of 40,000 atoms is as long as the diameter of a hair. How does a STM work? The minute size of atoms requires special microscopes to study their properties. Optical microscopes don't have the required resolution. This deficiency is due to the use of light to image small structures. We use a scanning tunneling microscope instead. This microscope achieves its unsurpassed spatial resolution by exploiting the quantum physical phenomenon of tunneling of electrons. If the tip of the microscope is positioned very close to the sample, a current of electrons flows, which depends dramatically on the distance between tip and sample. Image acquisition by a STM. The scanning tunneling microscope exploits this dependence of the tunnel current on the tip sample distance to obtain height profiles of the sample. To this end, the tip is scanned line by line over the surface of the sample, and the tunnel current is measured. If the scanning tip encounters a step on the surface, the tunnel current increases due to the smaller distance between tip and sample. A sequence of line scans provides an image of the topography of the sample. Imaging atoms. The high resolution can be used to image individual atoms in the surface plane of the sample. We resolved the atomic structure of a copper crystal. Our images reveal that the copper surface can be modeled as a close-packed arrangement of hard spheres, which are spaced at a distance of 0.22 nanometers. Imaging electron density variations. The atomic contrast resides on smoothly varying background. Typical modulation lengths are of the order of 1 nanometer, 5 times as long as atomic distances, and they're due to variations of the electron density within a surface. The tunnel current depends also on the electron density of the sample. Therefore, investigations of the electronic properties are possible. We study how the electron density varies due to electron scattering processes. We observe a wave-like modulation pattern of the electron density. Its characteristics are described by the laws of quantum physics. Electrons can be confined within a nanostructure, where they're scattered back and forth between the boundaries of the structures. A modulation of the electron density results due to this scattering. These electron density modulations get more complex with increasing electron energy. The analysis of these patterns offers new insight into electron dynamics in nanostructures. Our results help to understand how and why the electronic properties of a nanostructure differ from those of larger size samples. Atomic manipulations. The scanning tunneling microscope is also a unique tool to create atomic structures on the nanoscale. The atom can be transferred to the tip and transported along the surface, moved with the tip to another position. Atoms can even be arranged in an arbitrary manner. This way, atom by atom, the letters MPI are formed, which is the short form for Max Planck Institute. This is a very small name tag. Its length is only 4 nanometers.